Tonight I'm going to be trying to show you that this 9-factor product, and each of the factors is 8 digits, okay, but there's 9 factors here given by the pi product notation. Now, first of all, there are 9 factors. Notice the indexing starts at 0 and ends at 8, so 0 through 8 is actually 9 iterations, if you will. Okay, and this is an 8-digit number, and we want to show you that the product of these 8-digit numbers, these 9 8-digit numbers, is actually divisible by 73. Now, another way of stating this is modular arithmetic form or congruence arithmetic form. This says S is congruent to 0 modulo 73. That's equivalent to saying that S is equal to some multiple of 73. Okay, same thing. This means the very same thing. Technically, this says S minus 0 is divisible by 73, but that's just the same thing as saying that S is a multiple of 73. Okay. Now, I've written out a few of the terms here. And again, there are 9 of them, but this would be the one that corresponds to I equals 0. This guy right here is the one that corresponds to I equals 1. Right here we have I equals 2. And this would be all the way out to I equals to 8. Okay, so you can see that makes it a little bit more clear. There are 9 factors. I use the ellipsis here just because of space constraints. All right. Now, you're going, well, what do we do with something like this? You expect us to multiply this out? No, I mean, that would, inordinate amount of time to do manually. You know, obviously nobody would want to even take on multiplying 2 of them together, all right? So what we expect is going to happen here is that just one of the factors will be divisible by 73, or we will show that one of them is. Okay, that's the idea behind this. All right, now, you may notice right here, this one has a factor of 3. This is divisible by 3. If you sum the digits, you get 15, and that 15 is divisible by 3. So this one is divisible by 3. But that's about as far as you can get manually, I think. And also, you'll notice this one is divisible by 2 and 5, right? But after that, you know, it's tough sledding. Now, this is the one that is kind of special. You can rewrite this 11 billion, what is it, 111,111. You can rewrite it this very convenient way. All right. Now, you'll notice that this is the very same thing as 1,011 times, and this is the fun part right here, 10,001. Now, if you're wondering where this 1 came from, remember there's another 1 in front of this, right? Put a little dot there. Okay, and again, just it's distributive property. Okay, this really would read, if you wanted to show the extra step, this would read 1,000 plus 1, right? Okay, now what's so special about that? Well, we're going to try to show, it turns out, and again, this you'd have to explore this on your own, but it turns out 1,000 or 10,001 is divisible by 73. Now, if you don't believe me, let's verify that. Okay, we'll do 73 all the way back to 3rd grade, folks. Okay, now we anticipate, if I know what I'm talking about, we anticipate getting a remainder of 0, right? Okay, and then just as far as keeping the places, you would have to put the 1 in this position right here, the 100s position, the 10 squared position. Okay, and that would give you a 7,300 directly underneath here. And I won't try to talk you through every last step of this long division. Okay, and again, this is the same thing as saying 100 times 73. That's the position we're in right here. Okay, now when you now you have to subtract. So you get 1 here, 0 here. You'd have to borrow, so this would be 9 minus 3, which would be 6. And then you would have had to borrow from 10, so you would be left with 2601 right here. Okay? Now what do we need? Okay? Well, if you look at this carefully, you need a 3 right here. 3 times, it's equivalent to 30 times 73, but that's exactly the same thing as, let's see, y'all, this should be 27, right? Let's erase that. Right? 27? Yeah, 27. Sorry, you didn't have to borrow there, did you? Okay, so this is 27. Right here, 27. Now what do we need? Okay, we need to multiply by something to get rid of this. Now that something would be 3, and you get 2190 when you perform that multiplication. Okay, same old thing right here. When you subtract right here, folks, you end up getting 511. I must have made the pen bigger. Okay, and then to close it out, you need a 7 right here, because 7 times 73 is this number. Okay, 490 plus 21, right? So you see, folks, we got a remainder of 0, which means that this is the same thing as 1,111 times 73 times 137. So we even got more. We could have, it's divisible by 137 also. But you see, this means it is a multiple of 73, right? This means that this would be a multiple of 73. We can write this as, and I won't, it's clear, but we could write this as 73 times, I'm not going to go to the trouble to multiply that. It's because we don't have to. We already have that it's a multiple. That's all we need. Okay? And so it's QED time. Now, I did a video very recently about something very, very similar to this. Okay? So we have showed it's a multiple of 73, which, remember, was our goal. That we've shown this sum is a multiple of 73. We actually produced the m without finding out its Hindu Arabic numeral form, okay? But that proves it. And again, it took a special kind of situation here. You couldn't, I'm not trying to say that any 9 consecutive numbers in these magnitude ranges would be divisible by 73, but we got lucky. This number right here, this magical constant popped up. Basically, you're not getting this with the other factors that I know of. As far as I know, 73 is not a factor of the rest of these. I haven't checked them all. I know 73 is not a factor of this. I know 73 is not a factor of this. But we've just shown that this is a multiple. This guy right here is a multiple of 73. And all you need is 1. It's multiplication's a lot easier than addition, right? If it's addition, it wouldn't be enough just to show that one of these. Okay, but it is a product, and so the mere fact that 73 appears anywhere in this long concatenated product of 8-digit numbers means the whole thing has to be a multiple of 73, and we proved what we set out to prove. So that is all.